Alright, so this morning, it's just an extension of yesterday, so inclined plane. Inclined plane and use of IJ notation. Alright, so with I and J, usually we would use vertical and horizontal. So horizontal we would normally go for the I, vertical you normally go for the J, but we don't have to. So usually I and J represent the horizontal and vertical. Directions. Alright, however, if we've got, so when we've got something like this, where we've just, again, just got a horizontal, like the ground or something like that, we've got our box or our object sitting on the ground, we might then have some force acting on it. Then it makes sense for us to use horizontal and vertical directions and call them in terms of I and J, and then we can, with this vector here, would have an I component and a J component. However, we don't have to be stuck with horizontal and vertical. We can tilt those axes if we like, and when we got inclined planes, for example, it might be more convenient for us to do that. Spell, don't worry about that. There's no IE in there, just E. Yeah, that's not right either. There's no T there. Words. That's better. Alright, might be more convenient to use a different other references. Alright, so here's an example. We've got an inclined plane here. We've got our box sitting on that inclined plane, and as we know, things roll down the hills, so it's going to move this way. So this might be more convenient for us to change those I and J directions, and we can have one that's parallel to the plane and then the other one that's perpendicular. So we might have I runs this way and J perpendicular to that. Alright, and so that might be more convenient for us to do that, because it will then simplify our calculations, because we can look at what goes that's going to move in the I direction only, and then in the J direction there's going to be equilibrium of forces in that direction. So by doing that here, it's going to make the calculations more simple than if we had just gone with horizontal and vertical. for the I and J directions. Alright, so in the case of an inclined plane, parallel and perpendicular to the plane are more convenient. There we go. All right. So we'll do a couple of examples. So the first one, example we'll do where we just have something horizontal, and the second example will be on a plane. So text, example 14. Text, page 546. Alright, so here it is. Let me. So it says a block of, excuse me, block of mass 10 kilos is pulled along a horizontal plane. So horizontal, and a block of 10 kilos. So there's our block, 10 kilos, by a force of 10 Newton. Inclined at 30 degrees to the plane. The coefficient of friction between the block and the plane is 0.05. Find the acceleration of the block. All right, so there are, on my diagram, some other forces. I've only just drawn one force in there. There are some other forces. There's the weight force of the block, which is mg, 10 times 9.8, 98 Newton. There is also a normal reaction force, and because the weight force is acting at 90 degrees to the surface, a normal reaction force and the weight force will be equal. And then of course we've got some friction. Alright, and so what we know is that friction from yesterday is mu n, and so that's 0.05 times 98, which according to my calculations comes out to, no, I haven't calculated. Alright. Alright, so get the calculator out. .9. All right. So if we're going to look at is I and J, for example. Use a little key there for I and J. So because of the way I've drawn it, and I've drawn it pointing that way, it means this is positive, or anything that's in the other way, the direction is negative. So what we can then do is we can split it up into two bits. So in the I direction, what have we got happening? Alright, so that's horizontal. So this is where we need to split up our force that's at an angle into two parts. And so in the I direction, the resultant force, actually I've made an error with my normal reaction force, and then with this I've made an error. What error have I made? What have I forgotten to take into account?
The other board.
Yeah, this here, haven't I? Alright, so we'll get back to that in a minute. So I have forgotten to take into account this component of that 10 Newton force. So my normal reaction force in this case is not 98, but the normal reaction force plus this bit here would be 98. Alright, so in the I direction, let's get back to it. So in the I direction, we've got, in the positive direction, we've got this component, which is 10 cos 30. And in the opposite direction, we've got friction. And that equals to our mass, which is 10 times our acceleration. Alright, so we need to find out stuff about our friction. And to do that, what we are going to do is we are going to look in the J direction. Alright, so again, even though I'm assigning things as I and J, I'm still splitting it up into those and working independently with those. So in the J direction, so in the J direction, I've got, in the up, I've got two forces. I've got the normal reaction force, and I've got that vertical component there. So the normal reaction force plus that vertical component, which is 10 sine 30. And that's got to equal 98. Because they're in equilibrium. Alright, so 10 sine 30 is 5. So our normal reaction force is 93. Alright, so now our friction then is 0.05 times 93, which is a little bit less than what 0.05 times 93, 4.65 Newton. Alright, so now we'll come back to our I direction, and now we can put that back in our I direction. So back to the I direction. And so then 10 cos 30 minus the friction, which is 4.65, equals 10A. And A then, once we do that calculation, find that A is equal to 0.401, and it will be I, and metres per second squared. Alright. Alright, so don't try and rush through it like I did and then make a mistake. Alright, so this vector, because it's an angle, has a contribution in the I direction and also a contribution in the J direction. So in this case, because of that, these two things are not equal. But up and down will be equal. Alright, so that's horizontal. Let's have a look at one that is on a plane which slopes. We'll get that out of your textbook as well. Example 15. Page 547. Turn that off now, I turn it back on. Alright, there it is. Particle mass 5 kilos. Lies on a smooth plane inclined at 30 degrees. Alright, so there's our 30 degrees. Here's a different colour. Here's our 5 kilo mass. There it is. All right. There's a force of 15 Newton acting up the plane. So if it's acting up the plane, we're going that way, that's 15. Find the acceleration of the particle down the plane and the reaction force R. Alright. So they haven't actually mentioned anything about friction here in the text. And if they haven't mentioned anything about friction in the text, there isn't any, and also they've used the word smooth here. Alright, so we ignore friction. So the mass is 5 kilos and no friction. Alright. So in this case, if we're going to set up directions, again we'll use the along the plane and perpendicular to the plane. So, and seeing as in the question they've indicated it goes down, it really doesn't matter. But I'm going to do the positive direction of I down the plane and the positive direction of J perpendicular to the plane. All right, now this thing here then, what forces are there acting on this other than the one I've already drawn there? Well, it's sitting on something, so that thing's going to be pushing back, and the other force that acts on this is our weight force. Alright, so this object here, these are the three forces that are acting on that particular object. Alright, so there's no other forces acting, just those ones. Now the 15 is totally in the I direction, the N is totally in the J direction, but this weight force is at an angle. So what we need to do is we then need to split up that weight force, and we could split it up in all sorts of ways, but for us, if we could split it up into two components where one of the components is in the J direction, the other component is in the I direction, it's going to make our life a lot easier. Now, through geometry, if this is 30 here and the weight force is acting straight down, that'd be a right angle, so that'd be 60 in here. So this angle there then, because that's a right angle here, then that angle in there is 30 degrees, the same as this angle down here. Alright, so on the inclined planes, when you're splitting up your weight force, perpendicular and parallel, the angle here and the angle here will always be the same. Alright, from geometry. Alright, so what do we got? Our weight force, our weight of our thing is 5 kilos times 9.8, so that's 49 Newton. This component there, well that's adjacent to the angle, so that's cos, yeah, so 49 cos 30, which comes out to be 42.435. And this one down here is opposite to our angle, so that's 49 sine 30, which comes out to be 24.5. All right, anything about that so far? All right, got to be a little bit careful when you're doing that so you don't lose things. No friction involved, so I don't have to worry about that. Alright, so there's what we know so far. So let's check back to here. Find the acceleration of the particle down the inclined plane and the reaction force. Alright. So when they're talking about the reaction force, they're talking about this one here, and the normal reaction force, so the reaction of the plane pushing on the thing there. So N, just a note. So reaction force, short for normal reaction which is N. Alright, just so you know how to interpret that, because I've used R here, not N, so I don't want you confusing that with the resultant force. A reaction force, not resultant force. So just be careful there. Alright, let's have a look. What do we got? So if it's going to be accelerating, or it's going to be moving down the plane here in the I direction. So let's look at some I direction stuff. Alright, so in the I direction, so down this way is positive. Alright, so what's down this way that's positive? It's this component of our weight force. So it's the 24.5. Right, so just before I do that, what am I doing? I'm doing the resultant force is mass times acceleration. And the resultant force is that 24.5. And also in that direction we've got this 15, but the 15's up the plane, so if I'm saying that 24.5 is down the plane, which is positive, then I'm going to take away here. And that's 5A. And so in this case, there's no friction. We're told it's smooth, no friction, so we don't have to take that into account. Again, it's more complicated if there's friction. This time I don't have to worry about that. And so that would be 9.5 equals 5A. And so the acceleration would be 1.9, I believe, I metres per second squared. All right. So now we need to move to the J direction. And again, we can do the same, that the resultant force in the J direction is mass times the acceleration. Now, in the J direction, what's the acceleration? Not a trick question. If it slides on the plane, then the J direction's perpendicular to the plane. The acceleration would have to be 0, wouldn't it? In the J direction. Because if it wasn't 0 in the J direction, it'd move up or it'd move off the plane or through the plane. Alright, then it only moves horizontally. Alright, so what are our forces? So we've got our normal reaction force minus this component of the weight force. It's at 90 degrees, so it's 42.35. 435, not 35, 42.435. And that equals 5 times A, and of course A is 0, n minus 42.435 is equal to 0, so our normal reaction force in this case is simply 42.435. J newtons, except what do I need if I'm going to do J with that? I need to, no, it's up, isn't it? So it's right. So I just got to make sure I've got the direction right, and yes, because of the way I've set it up and the way I've written it, comes out as a positive, which is correct. All right, anything about that stuff? No? All right, so that's 13C.